All right, so yeah, welcome to this presentation. My name is Andrin, and I'd like to introduce you to a PHP implementation on GraalVM, something I've been working on over the last couple of months. So in this work, we present the design and implementation of a Truffle-hosted language implementation for the PHP language, with the main aim to perform a preliminary peak performance comparison of our implementation with the state-of-the-art of PHP. And thereby we achieve performance gains of more than 800%, 859% compared to PHP's reference implementation. So the PHP programming language is a popular and widely used language. It is typically rated in the top 10 languages by language ratings. It is further a dynamic and weakly typed language. Dynamic that types are only known at runtime, and weakly typed, meaning we can do things like adding strings and numbers. And PHP's reference implementation, Zen engine, implements the language with a bytecode interpreter that currently does not feature a dynamic compiler. So there is a fundamental challenge in implementing dynamically and weakly typed languages, because even for simple operations, there is an overhead. So to give an example, in PHP, we can do things like adding integers and strings and float and boolean and so on and so forth. And a implementation needs to type check these types in order to select a implementation. And so we believe that many existing language implementations, they do not apply aggressive optimizations in order to tackle this problem. So when studying previous work, we distinguish between two main categories that previous work did in order to accelerate PHP's performance. There is a source-to-source approach, where PHP is translated to a typically statically typed language, such as C++, for instance, and then rely on existing compiler technologies for optimizations. They use static analysis on PHP in order to infer types. Another approach uses a dynamic compiler in some shape or form, where a dynamic compiler gathers profiling feedback at runtime and then compile frequently executed code segments to machine code. I'd like to pick two examples here of language implementations for PHP. HHVM, the runtime, the hip-hop virtual machine for the hack language, a fork or a dialect of PHP, as well as JPHP. They use a JIT compiler, and we will see these implementations in our evaluation later on in the presentation. So our approach is similar and different to previous work. It's similar in a way that we model PHP as a Truffle AST, and then rely on existing technology, Truffle and Graal, for further optimizations. It's also similar to a dynamic compiler approach, because we use a dynamic compiler, we use Graal. However, it's different to previous work by modeling PHP as an AST, an AST interpreter, and use that as a means of gathering profiling feedback for JIT compilation. So as I said, we rely on two research components, Truffle and Graal. They are developed by Oracle Labs, and I like to show how these components interact with each other with a short example. So the idea of Truffle is to model PHP code as an AST interpreter and use that as a means of gathering profiling feedback. So to give an example, here we have a PHP snippet, a addition, and now we build an AST, and at some location in the AST, there is an addition note that corresponds to the addition in the code. And what's now distinctive about a Truffle AST is that we provide different specializations for these nodes. And these specializations, they make certain assumptions about the types. So for instance, we may provide a specialization which assumes that the input is integer-based or float-based or string and so on and so forth. And then at runtime, a truffle tree selects a specialization which matches the given types that occur. And this, the purpose of this is to gather profiling feedback for the second research component, which is Graal. So at some point, this tree selection, this specialization selection in the AST stabilizes. And then what Graal will do, Graal will inline all execute methods under the same tree to increase the scope to reason about, and then can perform optimizations such as constant propagation, constant folding, for instance, and JIT compile this chunk to machine code. Now, this is only speculative. So we assume that, for instance, in this chunk of AST, the addition is only performed with integer types. And if these assumptions no longer hold, Graal can de-optimize and fall back to the Truffle AST to gather new profiling feedback. And so a key takeaway is now here, or one of the key takeaways, is that in this inline scope, we no longer have to type check for every single operations, because we assume that, for instance, it is only performed on integer types. So having that said, we can present our implemented architecture. It consists of two main components. We have a parser and our language implementation. So we forked a parsing library. We forked the Eclipse IDE for PHP because we were unsatisfied with parsing libraries in Java. And we demodularized their parser to be a parsing library. Then we have our language implementation. And a simple use case would be we use our parser to parse a source file and then build a Truffle AST. Then during profiling, this AST rewrites itself and yields profiling feedback for Graal to JIT compile the AST. So when determining the scope of this project, we systematically analyzed popular benchmarks by the computer language benchmark game. These are often used by VM authors as optimization targets because implementing the whole specification was not feasible in the scope of our work. So what we've done is we analyzed benchmarks and selected key language features that were used in these benchmarks. We implemented data types, functions, and variables, control flow, as well as auxiliary operations, such as arithmetical operations, for instance. And due to time constraints in this presentation, I'd like to zoom into challenges we faced for implementing arrays. So arrays in PHP are a facade for various data structures. They can be used as sequences, map, stacks, queues, and nestings of these. And arrays in PHP are further untyped and dynamic, so they can grow dynamically. And while this is comfortable from a user perspective, because there's one API to interact with these data structures, it imposes some challenges for an efficient implementation. And so I'd like to introduce how we implemented sequences. So as comparison, ZenEngine implements arrays with a untyped hash map. And what we want to do is we want to implement them as specialized uniformly typed arrays, because often arrays are used in a uniformly typed manner. So what we do is we assume a certain type and then generalize if these assumptions no longer hold. We model arrays with a capacity and a backend, and then behind the scenes replace this backend if what we assumed doesn't hold anymore. In the scope of this presentation, we implemented two storage representations for our sequences. We have primitive long-based arrays and then object array-based backends. And while I can only go into detail, into high-level information, I still want to show some code. So we implemented arrays with a Truffle feature called Truffle Libraries. Truffle libraries allow us to perform or to have a polymorphic dispatch and caching for our arrays. So what we do is at runtime, we, based on the types we have in our backend, we can select at runtime a Truffle library, which then can handle our storage representation. Truffle libraries, they can be understood as Java interfaces in a way, by together with Truffle's domain-specific language, allow us to model a set of messages we want to support, and then implement a set of implementations for these messages. So I'd like to show one of these messages, which is the write message, to write into our arrays. And we have here a implementation of a library which assumes that the storage representation is long-based, so primitive long array-based. And so we see here, we assume that the input type is a primitive long, and then a array write is then simple, a primitive array store. Now, this is only, so we assume that we write into primitive long arrays, but if this doesn't hold anymore, so for instance, if you want to store floats into this array, this cannot work anymore. So what we have to do is we have to generalize the backend, copy all entries, and then select a representation that can host all values, including the new one. And so we implemented libraries in a way that allow us to have constant amortized complexity for read and write. This should give some high-level overview about the implementation. Now, when approaching our experimental evaluation, we tried to be very rigorous. So we provided a container environment which freezes all dependencies and stores our timing values into a database. We also open source that database in order to account for the variabilities across benchmarks. We execute the benchmarks consecutively within the same Unix process, as well as across multiple processes. As I said before, our main metric is peak performance. So we manually inspected our timing values and picked a warm-up threshold of 5 iterations. And we run between 25 and 140 iterations for each benchmark and each implementation. Some benchmarks took rather long, up to 30 minutes for a single iteration. We further enumerated minimum, maximum, mean, standard deviation, and confidence interval. And as I said, the computer language benchmark games are used as benchmarks. So here we see the first benchmark, Pfannkuchen Redux. To describe the axis, we have speed up on X and implementation on Y. Larger is better. We have Zen Engine PHP version 7 as baseline, as well as our implementation. So there is a JIT compiler announced for the next version of PHP, PHP 8. So we also compiled their alpha version and included it. And then I mentioned these two in the beginning. And then we have a ahead of time compilation of our project using a third-party library called SubstrateVM. SubstrateVM allows to ahead of time compile Java bytecode to machine code. We also included into the evaluation, but we did not further experiment or optimize the ahead of time build. So in Funcom Redux now we see a peak performance speed up of 859% or 9.58 compared to PHP's reference implementation. In SpectralNorm, we introduce a color code. So we have again, as before, blue, the copy by value version, so the default benchmark. And then we have new green, a version of the benchmark which uses PHP's reference operator. So PHP allows to copy arrays by reference, or values in general by reference. And we introduce these two versions here in order to show the potential of a more sophisticated array implementation, because by specifications, arrays are copied by value. And it's up to the implementations for optimizations in order not to copy by value all the time. So here again, we see PHP 7 as baseline, and then our implementation in the default version, blue, with 652%, and in the copy by reference version, 655%. So there's generally no big difference between these two versions because this benchmark doesn't heavily use arrays. In binary trees, we do see a difference between these two versions. So we see again PHP 7 as baseline. And if we can apply copy by reference behavior, we exceed PHP by 511%. But if we have to copy all array entries by value, so for instance, in function calls, function returns, or assignments, we are worse by minus 84%. And so future work will also include a more sophisticated array implementation, which, for instance, implements a copy on write implementation. And then we can automatically distinguish between copy by reference and copy by value behavior. So we see competitive results in this subset of the computer language benchmark game. We implemented a subset of the language specification of PHP with around 4,000 lines of Java runtime code. In future work, more research and engineering effort need to be invested in supporting more language features and especially benchmarking a more realistic workload. So PHP is typically used for HTML-based rendering in web servers, and that's also part of future work. Another interesting future work is supporting PHP's existing range of native libraries as well. So we already got some attention online. So one of the core researchers of Graal shouted out to our results, and we got some stars on GitHub and upvotes. So we open sourced our code and our timing results, have a Docker image and continuous integration with around 100 unit and end-to-end tests. And in terms of wider impact, we hope to have laid foundations for future work, but also to contribute to PHP security, because so our implementation is hosted on a managed runtime, and it's a lot harder to exploit memory and logic bugs on a managed runtime, because ZenEngine is written in C and has been subject to exploitation in the past. And so this concludes the presentation. If there's still some time, I see now I have around 19 minutes. I can show a short demo of a Mandelbrot calculation.
Yeah, that would be great.
Cool. So let me see if you can see that. So we have a Mandelbrot set. So what it does in detail is not relevant, but it calculates the Mandelbrot set. And we have two versions of this Mandelbrot set. I'm just going to diff them, because in one we have a built-in function to print a new line, and the other one in PHP we use echo directly. And so PHP version 7, that's the current version of PHP. And we have our implementation. So what I'm just now going to do is I'm going to run the Mandelbrot set. Then we get some idea of the speed up visualized. So on the left, PHP 7, and on the right, our implementation. And I can also show the same. So as I said, PHP announced a JIT compiler in the next version, which is slightly faster than version 7. So I can also show that quickly. To enter the container environment for that build. So we have PHP 8, version a alpha version compiled. So it is slightly faster than PHP 7. Yeah. And so this concludes the presentation.